Okay, so yesterday we started talking about flexural waves, right? And we derived the wave equation for flexural wave motion of a bar. And it's a kind of a difficult derivation, right? But we made our way through it. I want to mention quickly, I got hung up on something here. This is the neutral plane, right? So for small amplitudes, this is halfway between, which is reasonable. And at this moment right here, right along here, it's unstretched, right? Because the neutral plane means it's neither been stretched nor compressed. We have stretching up here and compressing down here. And this filament right here has been stretched some distance. This distance right here, which would be the equilibrium length, is obviously equal to dx. Right? When the bar's in equilibrium here, the length of this element is going to be dx, and that's what the length of this element is going to be. So I don't know how I got hung up on this, but this has to be dx right here, and this will be the distance in this case that it's stretched. Down here it'll be compressed. So we found this equation that's not the wave equation, because it's got a, here it is, it's got a fourth order in space. And because of this, the waves are dispersive. Different wavelengths or frequencies travel at different speeds. And what we want to do now is we're going to focus on standing waves. Okay, so these are transverse or flexural standing waves on a bar. And to do this, here's our wave equation. Okay. The standard way to look at this is to split the space and time, assume an e to the I omega t time dependence. It multiplies the spatial function here. This will be our search for standing waves. When we do this, when you plug this in, you're going to get 4 spatial derivatives on the spatial function here. This is going to bring down a minus omega squared, 2 time derivatives. So we get this. And this is now, of course, an ordinary differential equation. That's why this is not a partial. This is just a function of x. We've now gone to a ordinary differential equation. Remember the phase velocity is what we did yesterday towards the end. The phase velocity is for a wave of definite wavelength or definite frequency. It's the speed of that wave. It's the distance divided by the time, and that's what this is right here, as I reminded you yesterday. So for flexural waves, the phase velocity is, from the dispersion relationship here, we get this. Either of these expressions are equivalent. So we have a wavelength-dependent phase velocity. And we can write this, we can make this a little simpler by, you'll notice if you solve for Kc squared here and substitute it into here, we get this. So this is what we're going to use, and we're following KFCS on this. This is a little simpler, but I need to remind you something here. This V here, which is the phase velocity, depends upon the frequency. Okay? So we'll eventually have to pay a little bit of a price for this, but I think it's best just to follow their notation. This is, I guess, probably the simplest form, but it's not a constant. It's frequency dependence, phase velocity. Okay, so we have this fourth order differential equation. How do we solve it? Well, the natural thing to do with just about all differential equations is try an exponential solution, right? We want to solve for this function of psi, this function of x here. So we're going to try an exponential solution, and this is not really written properly. I think it's best just to take the underscore off here and recognize that in general both of these are complex, right? We need to go, to get all the solutions, we've seen that we need to go complex, and you'll see it here. So 4 derivatives is just going to give us a gamma to the 4th, and we get the exponential back. And here we just get, we're not doing anything to this, we just get the exponential. The amplitudes cancel. In fact, the exponentials cancel. That's why we often try this as a solution for a differential equation. Because you always are going to get this back when you differentiate it. So we cancel it from the equation. And if we move this over here, this is what we get. All right, so what's the square root of this? You need to be careful here, because we're after the general solution, right? We're after a general standing wave here. When I take the square root of this, what do I get? I don't just get gamma squared is equal to omega squared over v squared. I have to put a plus or minus here. And you know that's true, because if you square this, the minus is going to go away. So we have to be careful here. We have these two solutions. And then when we take the square root of that, what do we get? We're going to get on top of that two more solutions, because I can take, when I take the square root of this, I'm going to get plus or minus omega over v, right? What happens when I take the square root of this? Plus or minus I times the square root of omega over v. So we have four solutions here. And incidentally, the fact that there are four solutions here, and this is a fourth order differential equation, are intimately connected. You maybe remember that from differential equations, okay, depending on the order of the differential equation. So a general solution here would be to take, complex amplitudes and take A, for example, some amplitude A times e to the I omega over v times x, then add that to B, another amplitude, times e to the minus omega over v times x, etc. We would get these four solutions. That's not convenient. And you might, I think it's somewhat reasonable that it's not convenient, because we're after waves here. We know we're going to get waves, right? Standing waves. And rather than deal with exponentials here, it's better to go trigonometric, as we have done in the past with strings. Okay, get these sinusoidal waves. But because these don't satisfy the wave equation, in this particular case, because it's a fourth order equation, we also have these solutions we have to deal with. So instead of writing out four terms, and theta here is just short for omega over v times x. Yeah, theta is just short for gamma times x, okay? Instead of having all these exponentials, we're going to, you can choose any functions. This is called a basis set, and they're kind of like unit vectors in some abstract space. We have these four different solutions here, and we can rotate our solutions. We can consider different, as long as they're complete, they'll describe in it, as long as they're independent. So instead of dealing with this e to the plus or minus I theta and e to the plus or minus theta, we're going to go trigonometric and hyperbolic here. So this is, you all know this, I think. And let me remind you about the hyperbolic functions here. This is the hyperbolic, this is definition. Think of this as a definition. Here's the sign. And these are all independent. We can just shift to this other basis here. So we're going to write the general solution. It takes up a whole line here. Here we are. Okay? So instead of the exponentials, we're going to look at functions of the exponentials, trigonometric and hyperbolic, and we get, here they are. And we've got these four solutions here. We have four independent parameters here, arbitrary independent parameters. And how do you determine those? Well, you need to know initial conditions or boundary conditions. We've got an infinite number of solutions here, right? Embodied by the fact that these are arbitrary constants, and they'll get nailed down by, in our case, by boundary conditions. And you'll notice here that we need twice as many boundary conditions as we had with, for example, a string or longitudinal waves on a bar, which is essentially the same thing. So remember, a string we would have be fixed. The simple ones were fixed or free at x equals 0, and fixed or free We have those 2 boundary conditions. We now need 4 boundary conditions. And you might say, well, you might think that doesn't make any sense. Don't we just need 2? Well, you'll see. You'll see why it's physically clear. You're going to see shortly, okay? Now, I want to say something here because it came up yesterday. James asked me. What we're doing so far is for an infinite bar. You should think of this, everything to this point, starting from the beginning of flexure waves, has been for a bar infinite in both directions. That's the way you want to think about it. You don't want to start to think about boundary conditions because you can easily be lost. So this is actually kind of a Galileo type thing, you know, to narrow something down and make progress and then make it more realistic, like we talked about before. It's the same kind of idea here. So far everything we've done here would be for an infinite bar. And we specialize to standing waves here. The wave equation to standing waves. So we need to talk about boundary conditions now. Okay. Now I need to remind you here, and we did a similar thing in strings and longitudinal waves, but it was just not, it wasn't very difficult. But here it's more difficult, okay? I want to remind you that along the way of deriving the wave equation, we derived these formulas for the torque, and I warned you that they would be important. We derived the formula for a torque, which we call M, in terms of the transverse displacement, y, and the parameters of the bar here. And here's the force, the transverse force. And I'm reminding you now because we need these for the boundary conditions. There are 3 simple boundary conditions. The first one is not real practical. Has anyone ever seen this before? So this is best called a pivoted bar, a pivoted boundary condition. And that says it all, right? It's pivot, it's free to rotate there. So what's the displacement here at x equals 0 for a pivoted bar? 0. That's easy, okay? That's no problem. But the fact that it's pivoted, you know, as opposed to, for example, clamped, how do we get that mathematical information in there? Well, I want you to imagine here we got this end of the, we're down here at x equals 0, excuse me, we're over here. We got this end of the bar here. And the only, the bar here to the right of it can exert a torque on there. In general, there can be a torque, right? What does the torque have to be on the end of a bar? There's no other forces on the bar except the bar to the right. If there were any torque on this face, what would its angular acceleration be? Infinite. Yeah, it has no moment of inertia. So it's just an infinitely thin piece of material, okay? It's nothing. So we've got to have no torque here. And that means, mathematically, no second derivative. So these are the boundary conditions for a pivoted end. And you see that it's natural here. We got 2. We have a duplicity compared to the string now. We have to deal with twice as many boundary conditions. So we're going to have 2 boundary conditions on the left and 2 boundary conditions on the right in general. And you can see because of the complexity here of the motion, we're naturally are directed to think about 2 boundary conditions. Okay, here's a common one, free boundary. So here y does not equal 0, but first of all, what's the torque? Can this bar be exerting any torque on this end face? No, nothing there to balance out the torque, so it's got to be 0. So we've got to have 0 second derivative. And now there's also, similarly, there can be no force because there's nothing there to balance out the force. And it has 0, it would have infinite acceleration in the end. So we look up here and we see, okay, that's 0's third derivative. Okay? So the conditions for the free end are this. Finally, the popular clamped end. Okay, and one of the distance learning students, Andrew, I think it was Andrew Mara, sent me a message today. You guys hear about the earthquake in Italy? Well, he said that he heard that somebody on the 2nd floor of this building that swayed a lot didn't feel anything. Does that make sense? Look at, rotate your, here's the building. And I think probably clamp, clamp should be a reasonable approximation. I don't know about Italian buildings, but at least in this country, I think they're essentially clamped. Or actually, sometimes, now they'll make them actually, it's better to make it easy, let them move. Okay? But one of the reasons that person may not have felt much is because you can see what's happening here. The clamped, first of all, it's y is equal to 0, obviously. But what's the next condition? This is not going to help you. Because we can have forces and torques, because we got this external influence here. But what does it have to have? What does the slope have to be here? Continuous. It's got to be 0. Yeah, the slope has to be 0. So consequently, something is swaying like this, you can see just from this right here that it's going to clamp down here. It's going to tend not to sway very much here. The other possibility is that it could have been a node. In an earthquake, you're going to excite many modes. And I doubt if it was a node, but it could have been. It could have been. I think more reasonable explanation is the fact that it was to be treated as clamped. Yeah?
I'm not really understanding how something on the second floor would be on the sort of clamped end of this oscillator that we're talking about.
No, so this analogous to the person being right about here, right? And all I'm trying to say is when this is clamped, this is not going to suffer much motion here because you're close to a clamped end.
So is the clamped end the base of the building?
Yeah.
So isn't that shaking though? I'm just not.
Oh, no. The building is going to sway a lot more than the ground motion.
Okay.
Yeah, right. Yeah. So you're right. This is going to be moving back and forth, but
it's kind of like when you were exciting it like this, where the hand was hardly moving.
Yeah, it's going to be you think of it as resonance. So I think what I should have said was the people higher up felt it a lot more than the person down on the second floor. Yeah, you're right. So there has to be some motion there because that's what's exciting it. There's going to have to be some motion. This whole structure right here is going to be moving, right?
Yes, but the people that they are in the ground feel the earthquake, so it's more logical to be on a node.
Because you can do research on that. I just don't think so.
I've been in one in Japan.
Yeah.
So I was with my wife, and the epicenter was way far away, but we were up on like the 30th floor, and got vertigo. We went down to the bottom. They're like, "What are you talking about?" And we're like, "We don't." And they're like, and then we looked it up, and there was an earthquake that happened I don't know, 100 miles away or something like that.
But the people down, so I
the bottom of the floor, they didn't, the concierge thought we were idiots.
Yeah.
Mainly because we were, talking to them in English, and they were like, "We don't understand you." But
yeah, so it's a relative thing. There's going to be, like Donald said, there's going to be some motion here, but nothing compared to this up here. Very small compared to that. Okay, now, so I guess this is, since we decided, I'm sure there's some mechanical engineers in here, just nobody wants to admit it. But anyway, so this is actually kind of interesting. This is mind-broadening. That's why I keep telling you guys, that's why we do it in physical acoustics. So this is standard for physical acousticians to know this stuff. And it's interesting, we got these two boundary conditions here, not obvious. We got this fourth order differential equation. So it's just good. It's good to have this experience. It sort of opens you up to different things, which will happen in sound and fluids. Trust me. Okay, any questions about that so far on that, the boundary conditions? Okay, so what we're going to we're going to spend the rest of the time looking at the clamped free case. So there it is. I've, of course, greatly exaggerated this, right? The whole theory here is for small oscillations. And I can't remember if I told you, I think I did. It is true that there's been a lot of work done on nonlinear oscillations of bars and stuff like that. There's a lot of work on that. And it was done by engineers because they had to do it. Because in reality, you're not always going to have these small amplitude oscillations, like the people in Italy can tell you. So anyway, here's our general solution. We're going to apply the general solution to this case for a finite bar. This is free. And this is clamped, x equals 0, x equals L. Here's our general solution. So I recommend, as I've told you before, always do the simple stuff first when it comes to this. And the simple boundary condition here is to look at x is equal to 0. And there we have to have y is equal to 0 at x equals 0. So at x equals 0, the hyperbolic cosine's 1 and the cosine's 1, right? And these vanish. So from this boundary condition, we find that a plus c has to be 0, which means c is minus a. So we can get rid of c. All right? Similarly, the next condition here is no slope, as you can see here. So I got to differentiate these things. That's going to turn a cosine into what? Minus sine, and a sine into a cosine, right? And what does it do with the hyperbolics here? It turns a cosine into a cosine and a sine into a minus sine. Into a minus hyperbolic. Did I get that? Okay.
Just does the same thing.
Okay, wait. When I differentiate this, I'm going to get the hyperbolic sine, right?
Correct.
All right, right. When I differentiate this,
Hyperbolic cosine.
yeah, there's no sine. That's what I'm trying to. I just know from experience that you you have to be careful with the signs, right? They don't carry over. That's what I was talking about, Alex. Right? Okay. So you want to be, always you want to be careful with this. Some of you are still learning that you need to be. When you do calculations, you just have to be. There's no flexibility on how careful you are. You have to be. You have to do it perfectly. Just don't make mistakes. But it takes some experience to do that. Some of you are still doing this. And all it takes is a little sign error. I don't think I should call it little. That's it. It's over. Okay? So you want to be real careful with this.
The universe is gone, right?
Yeah, with energy conservation, you can eat up all the energy in the universe. All right, so let's go ahead and get rid of, I think the best thing to do here is to, D then has to be, because we just pick up these terms here, D has to be minus B. So let's put that in. So now we're down to just 2 coefficients. That's nice. It's a lot better than 4. All right? Now we got to go to the other end. And we do this similar thing here, except now we got 2. This is going to turn a cosine into minus a. This is just going to change the signs of the trigonometric functions, right? What does it do to the hyperbolics? Something's bothering me here. Oh yeah, because this is, so we have minuses here. So when we take the 2 derivatives, these minuses are going to become pluses. And you can show that nothing happens to the hyperbolic functions. Okay, so again, you want to be careful. They're not identical under, when you differentiate them. So we get this for the second derivative. Now we got to differentiate it again and be careful with the signs, right? And we get this. So what's the natural way to look at this? How do we handle a situation like this? It looks kind of complicated, doesn't it? Well, we have 2 equations, and I don't really want to start talking about the unknowns, but you can think of this as A and B as unknowns. What's really unknown is the ratio. Remember we've talked about this before? But here's the point. The way you want to think about this is, and I strongly encourage you to, you can work around this, but this happens so much in applications that you just want to learn it, okay, or relearn it. So we want to think of this as from a matrix vector perspective. I got this vector here formed by the amplitudes A, B, and then I have these elements in here. I'm not going to take time to write them down, but you can see what they are from here. Here's going to be the first element. This is this one right here. And then this is going to be the second one. That's what they are. Okay? Now somebody tell me, why did I do this?
Suppose you solve the
Yeah, so what do we conclude from this?
Determinant. That's true.
Right. So what if the determinant of this is not 0? Because this is simple linear algebra. I think all of you, most of you you have a refresher in it here, right?
They are dependent.
Some kind of,
Independent.
it depends on what?
They are dependent each other. The changes and are independent.
Right. So has everyone seen this here? The USW students too? In some kind of like refresher math course?
It's been a couple quarters, so.
Okay, well, a couple quarters is nothing.
No, but yeah, we all.
Okay, all right. The distance learning students, it may have been quite a while, okay? But here's the idea. This is really useful. It's something you want to learn. Is what's critical here is the determinant of this matrix, which in this case is just this minus this times this minus that times that. So maybe I should. Let's just put something here. Okay, the determinant of this matrix, extremely useful quantity. The determinant of the matrix is alpha minus gamma is this. If the determinant is not 0, what can you do? You can invert this matrix. You can find the inverse of this matrix. It exists. And then you multiply each side of the equation by this matrix here, and you can solve for A and B. So what are we going to get if the determinant does not equal 0? What do we conclude? I multiply by the inverse.
A and B have to be.
A and B have to be 0. We have no solution. We have no solution. So, but that's not right. We know we're going to have we know we're going to have modes here, an infinite number of modes. So the only way out is the determinant has to vanish. And what that means, what's at the root of this, it means that these two equations are not, these two equations here, when the determinant vanishes, they are not independent. If they were independent, the only way you can solve them is with A equals B equals 0. And there are other ways you can see this. You could imagine solving this for B and substituting the result in here. And what you would like to do is, well, when you do that, if the thing that's multiplying A is not equal to 0, you'll conclude that A has to be equal to 0. And similarly, B has to be equal to 0. So there's different ways of doing it, but this is really the most compact, and I strongly encourage you to use this. And we will be using it again a number of times. So we set the determinant equal to 0. We take this times this minus this times this and set it equal to 0. That's what I've done here. And then, of course, at this point, you want to look for simplification. And it's remarkable here. It looks like this could be a mess, but if you multiply these things out, square this, multiply that out, it collapses down to just a couple of terms here. And the way we naturally, you can see this has to be 0, and the only way that has to be 0 is the hyperbolic cosine. I've dropped the arguments here just to save space, time and space, and put them back in the final result here. The only way this is going to be true is if the hyperbolic cosine times the cosine is equal to minus 1. This has to 0 out because it's got to be equal to 0. We have to have 0 determinant. So this is the standard thing to do, and it's much easier than going in and thinking about dependent equations, and it's just much easier to do. Now, so what's next? What kind of an equation is that? This is our equation. It's going to tell us what the frequencies of the modes are. That's what it's going to give us, the standing waves here, the normal modes. What's the next thing that you would think that you would do here? Yeah, see this, how this is mixed between sinusoidal and this is essentially exponential? It's a transcendental equation. It cannot be analytically solved. So you would think, okay, we're going to move one of these over. You can move the hyperbolic cosine over here. What's 1 over the hyperbolic cosine? Nobody knows. It's the hyperbolic secant. It has a name. And it's important. It's important. We were just talking about it, was it last week or the week before in the nonlinear course? I have this tutorial, right, that I told you about for Ph3119. It is going to be, did I tell you it's on the books for this spring coming up? 4459. There are no tests, just homework, and a lot of demos. And we do chaos and solitons. Solitons are localized waves that act like particles, and the most famous of them are called KdV solitons, and they are hyperbolic secant squared. So I know what these functions look like, because I know a lot about solitons. And we're going to talk a little bit more about that in a moment. But anyway, you could, the natural thing to do is bring this over here, and again it has a name, it's the hyperbolic secant, and then do the standard trick, right? The standard graphical trick. And then suppose you, with a calculator or on a computer, you found the solutions. Do you know what you're going to find? You have no idea, and I don't know how this happened historically. But if you did this, if you actually found the solutions, you would find that after the first mode, or maybe the second mode, they all start to look highly analytical, like waves on a string. Which just doesn't, that shouldn't happen, right? So somebody, I don't know who figured this out, but here's what we want to do next, and it's not at all obvious. It's not at all obvious. We want to transform. Instead of dealing with this argument right here, the omega L over V, we want to go to half angle. We want to use half angle formulas. And if you ask me why, you just have to be patient and see what it does. But it's remarkable what happens here. And whoever did this deserves a medal. Okay? So here, you've probably seen some of this before. These are half-angle formulas. If you have half the angle, you can trigonometrically or hyperbolically like this, you can express in terms of the full angle here. And it works, the reciprocal works too, or the inversion is, if you have, and that's what we're going to use, if you have some angle here, you can express the cosine of theta in terms of the half angle, theta over 2 like this. So these are standard trigonometric identities that don't look familiar to me. They probably look less familiar to you. But anyway, this is, believe it or not, this is what we want to use here. So let's transform our transcendental equation here, okay, and go to half angles here rather than the full angle here. So we use this and this, these expressions, we get this, multiply through, bring this over, look for simplification, right? And again, as similar to before, this collapses down to something much simpler than you might think. When you go through this and you actually do it in your head, this is what we get. And now, what we want to do here, and this is the natural thing I think you would say, is bring the tangent over here, it becomes a cotangent, right? And you want to do that. You don't want to bring the hyperbolic tangent, and look at the inverse of that, and you'll see why in a moment. So now we've equivalently re-expressed our transcendental equation here. This is what we started with. We've now transformed it to this. And this is going to show us why you get these analytical type looking results, which is bizarre. And the reason is this hyperbolic tangent. Anybody know what a hyperbolic tangent looks like? There are solitons that are called kink solitons that behave like that. The hyperbolic tangent of x, remember, it's going to be the hyperbolic sine over the hyperbolic, it's going to be, yes, that was right. It's going to be the hyperbolic sine, which is this, right? Divided by, so, you know, when you hit this kind of stuff, you don't have to run to the internet or something. You just do it. You know, if you're worried about it, you can check it. But so it's going to look like this. What happens when x becomes large? 1, right. So the hyper, it's going to look like, it has to be at x equals 0, it's 0. So it looks like this. So it asymptotes to 1 and -1. How does it asymptote? How rapidly does it approach here? Exponentially. So after, for this normalized unit here of x, you know, after x equals 1 or 2 or something like that, you're already really close there. And you just get closer, much closer. So here's the whole point of all this. Here we are, right? We just care about the positive x. So here's our typical graphical solution of the transcendental equation. And you recognize everyone now knows about the cotangent, right? You recognize the cotangent here? Sort of, it's a kind of a flipping of the tangent. Our modes correspond to these intersections here. Now, this is just a sketch, but it gives you the idea, the right idea. The right idea is that this curve here rapidly, exponentially approaches the asymptote here, like I said over there. So by the time you get to here, when you're out there pi, this is essentially right on 1. Okay? So this is the cotangent. We want to solve for the cotangent equaling 1. What's the cotangent of an angle equal to 1? What solves that? 45 degrees. Tangent of 45 degrees and the cotangent of 45 degrees are both 1. So again, this is just a sketch here. But out here, when we're near the asymptote, I know what the answer is going to be. It's going to be, you know, halfway between pi and 3 pi over 2. So it's going to be 5 pi over 4. Okay, it's going to be 45 degrees, or from here to here. It's going to be 45 degrees, pi over 4. Increment by pi over 4. Pardon me? And similarly, we can keep going. Here's another one, okay? Now, what happens when we get here? Well, according to our sketch, it's not bad. Okay, we'll get precise in a moment, but I just want to show you here, it's not bad. But you can start to see, according to the sketch, a little difference. What about this solution? What about the fundamental mode? Well, it's going to be significantly off, right? And I didn't do this carefully. These x's are supposed to represent 45 degree or pi over 4 increments here. This should really, see how it should be right about here? So if this continued here straight, we would have, you know, if the curve went more like this, we would have a solution right about here. The actual solution is going to be a little bit greater. The actual solution. And sure enough, here's, oh, before we get in, well, let me jump to here. The approximation here of just setting the hyperbolic tangent equal to plus or minus 1 works extremely well from the third mode on. It's not bad for the second mode. It's roughly 0.5%. It's less than 1% error for this mode right here. That's not bad. For the fundamental, though, it's about 20% off. And you'll see this is the approximate value minus the exact value. And you can see here that our approximate value, if I had drawn this more carefully, would be right about there. It would be less. So we confirm that minus sign in. So this is remarkable, and it's happening because it really has to happen. And I'm going to say more about that in a moment. This has to happen. And I'm going to explain it to you. And it's not in the notes, I noticed. Okay, so again, this is we could get the exact solution with a handheld calculator or in a computer, and after this, people don't have any reason to be any more accurate. It gets, because of the exponential approach, it's essentially exact. Yeah.
Can you go back one slide, sir? How do we pick up the plus or minus hyperbolic tangent?
Oh.
So we got 1 equals.
Okay, you tell me. Yeah, you have this. What happens when you take the square root of something?
Oh, we took the square root. Okay.
Yeah. And again, that's a manifestation that we're doing everything in the complex plane. So if you're doing purely real analysis, the square root of 4 is 2, I guess. You know, if you're just doing purely real analysis. But we're doing everything in the complex plane because it's so much more convenient. So you got to be aware that when you take the square root of something, you're going to get 2 solutions. In general, for any complex number, you're going to have 2 solutions. Okay. All right, so this is KFCS's notation, and I think it's a good one. Here's how we write this. And at first it looks kind of confusing. It probably looks confusing, but it is. I think it's the best way to represent the precise results, something we can work with. Our frequencies are going to be given by these specific values. There's the pi over 4, because that's the 45 degrees, right? We were just talking about. And then there are these pure numbers here. Here's the fundamental. And what we're going to get here, and you don't have to get too far along here, we're going to get odd integers. Okay, and that's because, you know, for example, here, this is pi over 4 plus this. Then the next solution is you have to go up here, and it's going to be at pi over 4 plus that. So if you just stare at this or write down something, you'll see that it has to be odd multiples here. And if you extend this all the way back, this would be 1. So there's this 19% error here. But look at this. This should be 3 according to our approximation. It's very close. Very close. Usually the difference is negligible, unless you're doing something very precise. And here people just don't even work, like I said. You have to be doing something extremely precise to worry about how this differs from exactly 5, because of that exponential approach there. So this is what I meant before when I say that I would love to know the history about who did this. You know, when this was first done, somebody may have, well, you don't know. You know, research is I always say it's not like what you see in the movies, okay? A Hollywood's version of it. Research is strange. Bizarre things happen, and people are led to conclusions by ways you can't imagine, okay? But it would be interesting to know that what happened here. It could have been that somebody noticed this and, you know, using this. Where is it? Somebody used this, where I don't think it's going to be apparent in here. Well, I'll bet it is. Maybe it is apparent how the solutions get simple once you get sufficiently away from the fundamental. Maybe it is. I don't know. But anyway, here it's just immediately obvious. It's much better to make that transformation. So this is a nice way to represent, and this is just the beginning, because now we have to pay the price over here. Remember, this V is a function of omega, and here it is. There it is. So we need to substitute this into here and solve for omega. And while we're at it, let's divide it by 2 pi and solve for the frequency, because this is what's useful experimentally. For example, the lab this week, Friday, you'll be dealing with these modes. Observing these modes. So we're going to go ahead and solve for the frequency here. This is the frequency spectrum, the standing wave, the normal modes for a, what type of bar are we doing? Clamp free, right? Okay. So when you track this along, we keep using this notation, and then because of the dispersion here, because this is not a constant, because V is not a constant here, these things lose their uniform spacing. This uniform spacing here that you get to very quickly after the fundamental, that's gone. They get farther and farther apart because of the dispersion. So that has consequences. For example, in an earthquake, you know, earthquake's going to excite a number of these flexural modes of a building. And those modes get farther apart in frequency. It means they're going to be harder to excite. So it'll tend to be more of a pure tone. So musically, if you played this, oh, and I was thinking about this. So this is another case. This has come up. Every class is different. Every time you teach the same class, it's not the same. So one of the things that emerged with this class is that it would be really nice to hear a bar where a lot of modes have been excited. You know, let's say by pulling it down and just letting it go, you're going to excite a lot of modes, right? And we can calculate that, right? So it would be nice to hear it. I think this could be easily doable on a computer, right? With a sound card, it should be able to play the tone. So you're going to get these higher modes with amplitudes that you've solved for. So you want to just play that, do the equivalent acoustics, just to see what it sounds like. And here, what's going to happen, because of the square here, and I think we're going to talk more about this tomorrow, because of the square here, you're going to tend to not excite these modes that you would have excited if they weren't getting so higher in frequency. So it's going to have more of a pure tone, not really be that interesting. But sometimes that's what you want. For a tuning fork, for example, that's what you want. Okay, now, nobody uses tuning forks anymore except in demonstrations, right? But they were used for centuries. You guys know what a tuning fork is? Okay. All right, so here's how we write it. This is a nice way to express it, I think. And if you want if you don't know, alternative to this, writing these things out, which I like this and I use it a lot, is you can see here that what we've got are these odd multiples again, right? So we can write that as 2n minus 1, where n is a positive integer. So we can write this like this, but the warning here is that you don't want to just take this and go with it and forget where this came from, right? Why? What happens at n is equal to 1? You're going to be off. So you have to be aware of this. That's actually one of the reasons that I like this. When you look it up, I prefer to deal with this. Okay, one more thing here. Sometimes people distinguish between the modes. Oh, now I need to tell you something. Yeah, about. Remember I made this strange statement? I said, we really have to have these simple, they have to be simple like this. Has to be. I'm going to give you an indication why that's true here. Here's the fundamental. Right? We know, now we just found the frequency, but you know it's going to look like this. You know that's going to be the lowest frequency mode. Having found the frequencies, now we can go back and look at the waveforms. But we know it's going to look like this, and we know that the next mode up is going to have one interior node. It's going to look like this. People do distinguish the nodes here because they're different. This has a node here, and it's not like a node on a string, is it? Going like this? No, it's stronger. It's coming in with always has zero slope. So that has the consequence that there's not much displacement here, as we discussed before. These nodes where y is equal to 0 and the curvature is 0, that's what happens for a sinusoid. That's what happens for waves on a string, right? If I got a wave on a string here, something like this, at this point right here, the displacement is 0, and what's the curvature? It's 0, because it's going from negative curvature to positive curvature. So these are sort of the normal, sometimes they're called the true nodes. I think that's what KFCS tells us here. And then there's the node once you're beyond the fundamental. Then there's this node. What's peculiar about that node? Can you see it?
Curvatures.
Yeah, this is going to just keep curving like that. Now we haven't proved it, but I think everyone will buy it. That's what's going to happen. But I'll show you some plots that I did tomorrow of this. But so here we don't have the zeroing out of the curvature. I didn't write it down here, but so these are considered to be, these look a little bit differently. But what happens when we get inside here? What do you think this is going to look like? It's going to look like sinusoids, right? You can see the nodes here. This is just a sketch, but I'll show you some actual computer plots tomorrow that I did. But you would expect this. So what happened to the hyperbolics? And I didn't comment on this here. What happened to the hyperbolics? In a sense, they're in there because you got to come up with these weird boundary conditions. That's the only way to do it here. The boundary condition here, and to come up with this end that's not coming in with zero slope, it's just flopping up and down like that. That's what in a sense, that's what the hyperbolics are needed. And they just contribute very little here. You know, they are hyperbolics, they're exponentially localized, or in this case, you know, we call it dark in soliton language, it's dark here. Their structure is exponentially localized, like a hyperbolic secant. Here, this structure it's a kink, and it's localized like this. So this is all very qualitative. It's hand waving, but it's interesting that the effect of the hyperbolics is going to be small inside here. It's just at the ends where they become prominent, and that's reasonable. I think that's reasonable, because if you have an infinite bar and you've got a nice standing wave on there, what's it going to look like? Oh, this is a good question. So now I have an infinite bar, no boundary conditions, and I have a standing wave. What has to be true about the solution? Let's go back. Where's the general? Okay. So we just want to look at the general solution here. We could go back to here. It seems to me, I'm about to make, I may be regretting this, okay? I may have to get Gene posted as a mistake. But it seems to me, I think I thought about this before, but I can't remember. It may be, I would think that the hyperbolics could be zero in this case. How can we prove that? Well, it's something to think about. I'll think about that. I'll let you know tomorrow. Okay? But it is interesting, and it's plausible, and it's kind of mathematically bizarre. But you can see from the sketches here that the hyperbolics are going to play a role for the boundary conditions here, but they really don't do much. They don't look like they do much here, interiors. So I'll think about that and get back to you on it tomorrow.